So I'm going to work fully through this electrolytic cell example. When you get questions, they may not tell you whether it's electrolytic or voltaic, but the layout, the structure should hopefully tell you. You're expecting 2 beakers, 2 half cells, unless there's a porous cup. There's no porous cup, there's no salt bridge, there's just 1 beaker, there's 1 solution. So we read through this example, you see a zinc sulfate solution, 2 electrodes in it, so your brain is sort of thinking electrolytic. You may not know fully till you do a bit more analysis, but there's no way that this is a voltaic cell. It just doesn't fit those standard pieces. So I'm going to draw this cell and then answer those questions. So the first thing we need to know is what's going on, what species do we have. So I've pre-made my list. We have 2 lead electrodes, so that's just lead. That's elemental lead. There's 2 of them, but I only put it on my list once. Then we have a zinc sulfate solution. So I put in zinc 2+, sulfate 2-, and the solution will be water. So we can label our OAs and RAs and figure out the chemistry. Lead is always a reducing agent. Metal ions are always OAs. Sometimes they're both, but zinc doesn't have multiple charges. Single charge metals are OAs only. Sulfate, we got to watch out for. I'm going to need my table. There's some pairing. Water, I don't have to look at my table. Hopefully you remember that's both. So what do we find with sulfate in our table? And we see lead in a few places. On the OA side, we see lead oxide, sulfate, and H+. But we don't have all those pieces. We don't have lead oxide, we got sulfate, but no H+. So this, we don't have all 3 pieces. So that's out. We don't have that second best OA. But on the RA side, we do have a pairing. We've got lead and sulfate together. It's at the -0.36 volts. We got lead, we got sulfate, we got that RA combo. So I'm kind of connecting them together to say those 2 are a reducing agent. We actually have sulfate showing up again. It's a very bad OA, but sulfate and water near the bottom of our OA column. So one reason I'm doing this example is just to highlight some of those lead or lead sulfate pairings you have to watch out for. What's our winners? We've got 3 OAs to consider. If you start at the top of the reducing agents and work your way down, we've got zinc 2+ is just above water in our table, and the water sulfate is lower even more. They're all pretty bad, but the zinc 2+ is the best. So our strongest OA, and the OA always reacts to the cathode. It doesn't matter the type of cell. And its reduction potential is -0.76. It's below our reference. Our best reducing agent, we've got lead. We got that lead sulfate pairing below it on the RA side, so that's even better. Water is fairly up high, so it's a pretty poor reducing agent. So that lead sulfate pairing is actually our winner. So if we missed it, it would be incorrect with our prediction. So we have to flip it from what's in the table. So lead, that would be one of our electrodes. Plus sulfate 2- anion. It's going to make lead sulfate. Now that's an ionic compound that's not going to stick to another metal. It's just going to precipitate out of our solution. And this cell potential is minus 36 volts. So I want to draw this, and what is the cell potential? So I can do that cell potential piece. It's the reduction potential at the cathode for the OA, subtract the reduction potential for the RA at the anode. When you do this, you get a negative 0.40 volts. Okay. This is an electrolytic cell. We got a negative voltage. It's not a spontaneous cell. Without a battery, the solutions, the chemicals will just sit there and do nothing. And that's what you see in an electrolytic cell lab. Until you hook up the battery, there's nothing. We'll have to talk about in our diagram. We have 2 lead electrodes. And an aqueous solution. We've got zinc 2 plus aqueous. We got SO4 aqueous. I just didn't write the aqueous in my diagram. Labeled it right in the solution. We're going to have our external cell, our wire. We've got our power supply. And we know we're going to need lead at the anode. So if there was only lead on one side, we would need to make sure that side was the anode. We got lead on both sides, so it doesn't matter. So you can set your charges either way. I'll make that the plus and that the minus of my battery, which will set the electrodes. So the negative is going to be the cathode. Positive is going to be your anode. So electrons are going to get pulled out of the anode to the positive terminal of the power supply and spit out the negative. Let's see, what chemistry is going to happen? At the cathode, zinc ions are going to make elemental zinc. And elemental metals will stick on top of each other. So we're going to have cations going towards the cathode, and then they're going to happen to be the reactant, and they're going to make elemental zinc at that electrode. So an elemental metal will stick to an elemental metal, so the bottom of that lead electrode will get coated. And that's how you could galvanize a nail. If that lead electrode was a nail, you could zinc coat it. Now, I only drew the zinc coating below the water line. You're not going to get any zinc up here. It can only coat in the solution. So if you wanted to coat the whole cathode, you'd have to submerge the whole cathode. At the other side, we've got lead and sulfate reacting. So we're going to have anions going towards the anode. The lead electrode and the sulfate are going to form a ionic compound, and that's just going to precipitate and collect at the bottom. So PbSO4 solid would be made at the electrode, but then it would just fall right down underneath it. So observation-wise, the cathode would be getting heavier because we're zinc plating it. The anode would be getting lighter because it's a reactant and we're consuming it. pH wouldn't change. There's no hydroxide or hydronium H+ in this. So it would be a neutral solution the whole way through. There's no colors on page 11 of our data booklet, so we couldn't color. But if an ion is made, that's on page 11, you could predict that color being made if it was a product or disappearing if it was reactant. That shows up on diplomas pretty much every year. You have to use page 11 to predict a color. So we got a couple questions to answer and we're done. What is the cell potential? Well, that's minus 0.40 volts. That's our barrier that's preventing this cell from running. What's the bare minimum voltage we have to put in from the battery? You would need at least the positive version of our barrier. So the bare minimum would be positive 0.0 volts. If you only put in 0.3 volts, that's not enough to force the electron. But you put in 0.5, you put in 1 volt, it'll work. For the assessment on your diploma or test, we'll always ask you for the minimum, the positive version of the cell potential. So that's electrolytic. It's a little more complicated than voltaic, but sequentially, you make a list, you find your strongest OA and RA, and then you just look at your chemistry to predict any observations. So E0 cell is the same as we've been doing it all along. Cathode sort of minus anode. So time for you to practice a bit. So I've got a few questions to work on. They're right up on the board. So 5 has a couple pieces to it, A and B, and 6, A and B, and 6 you get a bit of a weird answer. So I've restarted that and just warning you, when you get it, you might think you're wrong, but you potentially could be right. It's an atypical answer. So let's work on those. There is a little bit more on electrolytic cells to come. So you have one more lesson that deals with one exception. There's a time where your table makes an incorrect prediction, and you have to learn, well, there's many times, but you only have to know when chloride makes an incorrect prediction, and you'll learn about the chloride anomaly in your last electrolytic cell lesson.